Alright, tonight we're going to talk about three things: fusion, fission, and transmutation. So fission and fusion both fall under the category of nuclear power. And so when we talk about those, we'll be talking about nuclear power. Transmutation, on the other hand, just falls under the category of super cool science. Alright, the first type of power would be fusion. So what fusion is, as the name kind of implies, you're fusing things together. You're taking two lightweight nuclei, so two smaller nucleuses, and then fusing them together to form one larger nucleus. And the larger nucleus has to be under 56 nucleons. So it has to be two lightweight nuclei that form a medium-sized nucleus. So an example of this would be two hydrogen atoms. So here we have protium, which is hydrogen with a mass of 1, and here we have deuterium, which is hydrogen with a mass of 2. When we combine those two, or fuse those two together, we wind up with helium-3. And so you see, this is all like the other things. 1 plus 1 equals 2. 1 plus 2 equals 3. So we're taking two smaller nuclei and forming one larger nucleus. So the reason fusion falls under the category of nuclear power is because not only from this reaction do we get a larger nucleus, but we also get a ton of energy. And this is large-scale amounts of energy that this type of reaction produces. A very, very large output considering the small materials that go into it. In fact, we witness this every day, the colossal power that this provides. The sun. And so the reaction that's happening on the sun is just a giant fusion reaction. It's literally hydrogen bonding with hydrogen, fusing with hydrogen to form helium and a ton of energy. Step outside sometime in the sun and feel the power of that energy coming all the way from millions of miles away. Now, if we could figure out how to do fusion reactions on Earth, we could generate a lot of energy from very minuscule products. If you look at what's going into this, just hydrogen, and we're generating helium, that means very, very abundant products, and we're generating wastes. It's just helium, so we can pump it out into the atmosphere. It won't really do any environmental damage. However, if you think about where this reaction takes place, the core of the sun, tells you that this reaction actually requires large amounts of input. So unfortunately, this type of reaction requires high temperatures and pressures. Temperatures and pressures that we cannot achieve on Earth. There's no materials on Earth that can withstand the temperatures and pressures required to maintain this type of reaction. And next up is fission. So fission is actually just the opposite of fusion. In this case, we have a massive, so a very large nucleus that is split up to produce two smaller nuclei. And each of the nuclei that are produced, each of the daughter nuclei, will have 56 protons or less. The best way to show this being done is with a picture. So what happens with a fission reaction is it has to be initiated, it has to be triggered. And the way you do it is you take something like uranium-235 and you slam it with a proton. So you add an extra proton to its nucleus. What you create then is an even more unstable version of uranium, one that's so unstable that it will decay into barium and krypton and 3 more neutrons. So if we write this out as a nuclear reaction, we would show the one neutron, and we symbolize a neutron with a mass of 1, a charge of 0, and an N, and we're adding that to a uranium-235. When this happens, it turns into uranium-236, which is unstable. We're going to skip that and jump right to the products. So then it produces, in the end, barium-141. It produces krypton-92. And 3 more neutrons. And as always, the math still works out, so 141 plus 92 plus 3 ones, that would equal 235 plus 1, so 236, 236. Adds up on both sides. And then down here we've got 92, 56 plus 36 plus 0 also equals 92. And as with fusion, when this occurs, we generate a ton of energy. Although the output isn't quite as large for fission as it is for fusion, it does generate a lot of energy, a lot more than other fuel sources. The problem with fission, though, as a fuel source, is it uses radioactive materials as its fuel. Radioactive materials are inherently dangerous, and then these products that they create are also radioactive, and so you wind up with a radioactive fuel producing radioactive waste. So that creates some issues. But there is something cool about fission. If you look at its one product, 3 neutrons, so those 3 neutrons, after the decay, go flying off somewhere else. Where did they go flying off to? Well, let's take a look. So if we take a look at this diagram, this is what shows what happens then. So we have this 1 neutron that comes, hits the uranium. Uranium splits into krypton and barium, and then 3 more neutrons are produced. Those 3 neutrons can then go on to hit 3 more uranium atoms. Those 3 uranium atoms are going to split up into 9 more neutrons. Those 9 neutrons are going to go on to hit 9 more uraniums. Those 9 uraniums are going to produce 27 more neutrons, and it will keep going on. This is called a chain reaction. So if you have yourself a huge chunk of uranium-235, really, all you need is 1 neutron thrown in there, and the rest of the reaction will take care of itself. But 1 neutron doesn't just generate 1 more neutron. You see how it extrapolates every time, so after each decay, it gets larger and larger and larger, and it can expand to extraordinary amounts. This, ladies and gentlemen, is a nuclear bomb. So each of these decays produces neutrons, and it produces a lot of energy, and we get this huge influx of energy that they then captured to create nuclear bombs, but they also use it for what we call nuclear power plants. So last up is transmutation. So transmutation is a reaction that converts one element into another. So it sounds similar to the other nuclear reactions. The difference is this is man-made, so this is ones that we do on purpose. Natural occurring ones, alpha, beta, gamma, positron, electron capture, but this converts into different elements using man-made techniques. So on your periodic table, if you look at it, all elements after uranium are whited out, and they're whited out because they're man-made elements. The naturally occurring elements occur from uranium and before. And all of those man-made elements, the ones past uranium, we call transuranium elements. So it's elements 93 and on. One such transuranium reaction would involve uranium-238, and they bombarded it with 15 neutrons. So 15 neutrons, and that would produce something unstable that itself would release 7 beta particles. And as a result, we wound up with an element that had 253 nucleons, 99 protons, and the scientist who first did this experiment, first proved that they created it, named it Einsteinium. This is just one example of lots of transmutation reactions that they've done. All of them usually involve slamming it with some type of particle, and the particles aren't always neutrons. They can be neutrons, or alpha particles are just smaller nuclei. They can slam it with things like carbon or boron or nitrogen. And it usually ends up producing some type of decay, so beta decay or alpha decay, or just shoots off some extra neutrons, and then we're left with a brand new element. It usually doesn't exist for very long, it decays, but it gives scientists enough time to study that element and to learn more about the periodic table and the configurations of the nucleus. And these reactions are still being done today, and every time they succeed with one, or even don't succeed with one, we learn a little bit more about atoms and the tiny world that we can't see.